I don't see a ticker, but I think that I can probably start off.
300.
Uh, yeah, great. Hello, and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'm Margaret Ann Story, a professor of computer science and a Canada Research Chair in Human and Social Aspects of Software Engineering at the University of Victoria. And my research seeks to understand how software tools and theories can help improve how software engineers create software. And I'm super excited right now to see and shape how software engineering is evolving in today's world of generative AI. But before we get to today's exciting tech talk by Kent Beck, I do have a few details I need to share about this series of talks in the ACM. So, for those of you who may be unfamiliar with the ACM or what it has to offer, here is some more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. You can see some of the highlights on your screen. ACM provides access to ACM's digital library, the world's most comprehensive database of computing literature, leading publications and global conferences that draw top experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, and the ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals, excuse me, make ethically responsible decisions in professional practice. So before we get started, we'd like to quickly mention just a few housekeeping items shown on the slide in front of you. If you have any questions at any time, please type them in using Zoom's Q&A button. We'll organize the questions as Kent speaks and try to get to as many of them as possible. This session is being recorded. It will be archived. You'll get a chance to share it with your colleagues and friends later on. And you'll receive an email notification when it becomes available, and you can check learning.acm.org for updates on this and also other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it out because it does help the ACM improve the Tech Talk series. Okay, today's presentation is called Empirical Software Design, When and Why by Kent Beck. Very excited about this. I know you all are as well. Kent Beck is a world-famous software engineer and the creator of Extreme Programming, a software development methodology that moves away from rigid formal specification in favor of a collaborative and iterative design process that is more human-focused. Kent was one of the 7 original signatories of the Agile Manifesto. He pioneered test-driven development, and he played pivotal roles in developing software design patterns and CRC cards as a lightweight design technique. He further wrote the S-Unit testing framework for Smalltalk, which then spawned the X-Unit series of frameworks, and most notably JUnit for Java. And more recently, Ken authored a very elegant book, which I really recommend you read, called Tidy First, that talks about how and when to tidy your code in order to support sustainable software design. Very, very cool. There's a cool chapter at the end on theories as well. It's a must read for programmers, and I would also say teachers that are teaching programming, especially useful perhaps for those relying on vibe programming these days. So, Kent, without further ado, please take it away.
Thank you so much, Margaret Ann. What a pleasure to be here and talking to you all from I was going to say sunny San Francisco. It's gray and cloudy San Francisco, however, so I'll have to go with that. Margaret Ann mentioned that she has bright sunshine, so I'll just be jealous. Um, Today, I'm going to talk about software design and, in particular, going back to the roots. So the source, the text of what I'm talking about is this book here. And this is my actual college textbook with a bunch of post-its which hadn't been invented when I was in college, but I used them later. Um, and so I had this as a college textbook in 1980, 81, quite soon after the book had been published. In 2005, I was invited to be on a panel with the authors, Larry Constantine and Ed Yordan, blessed memory. Uh, and I thought, you know what? I should read this book. I'd been developing software for, I don't know, 30 years at that point. But since I was a college textbook, I hadn't read it. So I thought, let me read this book. So I started reading. And that's where the pink Post-its came from, was that second reading in preparation for not wanting to sound like an idiot on stage with Ed and Larry. I wanted to give them their due. And I was so excited. It was a page turner for me because what heard, what I read, what I finally understood was the equivalent of Newton's laws of motion for software development. And the original concept. So this was the book that introduced the words coupling and cohesion. And by that time, those words had become more and more diffuse, um, and people were using them to mean just kind of coupling as things go together and cohesion as things go together, and so whatever. But there were very specific definitions of those two terms in the book, and the terms had been derived from a study of early IBM software. Some software was easier to change and some software was harder to change. And they tried to sort the programs into two piles and figure out what was common about the software that was easy to change and what was common about the software that was hard to change. And they came up with coupling and cohesion as the two basic principles. So, I decided then and there, okay, I'm going to take the material in the original book and translate it for a modern audience. Because the examples in the book were about these newfangled higher level languages, and is C ever going to replace assembly language? And, how do you design a system with paper tape and so on? So I thought, okay, well, the examples need to be upgraded, but the basic concepts are absolutely essential for every software developer to understand. And as I got into it, I realized, and this is the source of the title of the talk, I realized that the disagreement about software design is much more about when and why than it is about what gets designed. There's designs that are definitely good, designs that are definitely bad, but people get to those designs in very different paths, and the path you take to get to the design is as important as the design itself. So let's start with economics. Much of the design advice that I'd seen uh, acted like all that matters were the technical constraints on design. And uh, I knew enough about economics at that point that I thought, no, you've got this ideal world of, well, I want to design good software, so I'm going to go do this and this and this. And it went counter to the economics of software development. And so those idealistic perspectives always lost. And it's because it just goes counter to the money. So I wanted a design style that was both economically superior from a human perspective, the flourishing of human creativity, and also met the constraints of software development as an activity. So there are three economic imperatives that we have to meet in any kind of software development. The first one is just survival. That is, if we don't get enough done that we can fund keeping going, it kind of doesn't matter what the design is. And this is where upfront heavy design tends to lose. Okay, so I'm going to spend 6 months designing this software, and then at the end of it, it'll be fantastic, except the money runs out after 3 months. It doesn't matter how fantastic it might have been in theory at the end of 6 months if you don't get to 6 months. And this is a concept of ergodicity. And I highly recommend the book Ergodicity by Luca Delana, to talk about. There's a big difference between decisions that mean game over and decisions that you can continue from. And design, the when of design is a decision that can mean game over. So, whatever the advantages or presumed advantages of designing earlier in larger, more speculative chunks, if that damages survival, it just doesn't matter if it turns out better, if it doesn't turn out at all. Okay, so let's assume that we've adopted a style of design that gives us a chance of survival. Now we have two competing economic imperatives. On the one hand, we have net present value, which is the money coming in and the money going out. Now it's the word net in there, or the word present in there. Net means we're going to add up all the money that we spend and all the money that we earn, and that should be positive. But the word present in there brings up another important aspect, especially as interest rates have gone up, which is if we can spend money later, it's the same economically as spending less money. So, two design styles, one of which pushes the investment in design out into the future, and the other which spends it now, the one that pushes the costs into the future is more economically valuable. And this is the time value of money. I won't go into greater detail, but there's a lot of material out there on net present value. So, and the converse is true. The sooner earning money sooner is the same as earning more money. So we would like a design style that encourages earning more money and earning sooner, spending less money and spending later. And that's the when of design that goes counter to a lot of the advice that I had heard. But there's a competing imperative, which is optionality. Why do we design at all? We design because we want to change the software. If you didn't have to change the software, you could have one gigantic million line main function. The software sits there and runs. You can charge money for it. You pay some money to operate it, and that's it. So, compared to a highly distributed microservices, but we're still not changing it. It doesn't matter. If we don't have to change the software, the design doesn't matter. And every time we change the software, uh, we are exercising options. The more different ways we have of changing the software, the more valuable it is. Imagine we have software that we're going to buy a software system. One of them, we spend $1 million and we earn $2 million, but we can't change it. Can't make any changes at all. The other, we spend $1 million, we earn $2 million, but we can change it in any number of different ways. Which one of those two would you pay more money for? Yeah, the one with the options. So every time we improve the design of the software, we're increasing the value and increasing the value based on the options of what we can do in the future. There's a bunch more to talk about that, some of which is in the book that Margaret Ann held up, some of which is in the follow-up book that I'm working on now called Tidy Together. So we would like a style of design when choosing when and what to design that maximizes the value of the software we create, that maximizes the chance that we'll survive, first of all, and that balances the net present value, the cash flows, and the options for future change. So here's an idealized, simplified version of software development. It's all based on change. We have some idea for how we want to change the software. And then we implement some feature. And part of the magic of software is that as soon as we implement the feature, we get a bunch more ideas for how we might want to change the software. And so all to the good. If this was all there was to software development, it would be simple, but it's not. There's another layer of what goes on. That process of going from idea to feature is can be very different depending on the structure of the software. If I have to go implement a feature, but I have to change 10 different files and I probably spawn 20 more bugs, that's very different than if I can go to one location, make one change, and then the feature is implemented. So sometimes the right flow of activities isn't going straight from an idea to a feature, it's going from an idea to a change in the structure. Let me rearrange things so it's easy now to implement the feature. And this is the tidy first flow of the book that Margaret Ann held up. Sometimes you have an immediate win. I could spend a week implementing this feature, or I could tidy for a day and it'll take me a day to implement the feature. Uh, and so that's the path I should take. Now, sometimes the savings don't come that immediately. You say, well, I'm going to spend a week on the structure and then I can implement the feature in a day. So I've cost myself a day immediately, but I'm going to implement a bunch more features like this in the future, each of which will now take one day instead of taking a week. So it'll sometimes it pays off over time. And this is where judgment comes in. None of this can be reduced to a simple set of rules. How we balance investment in features and investment in structure is something that you have to learn mostly by making mistakes. Now, this isn't the whole picture. Sometimes we go to implement a feature, we have an idea, we go to implement a feature, we think, God, that was harder than it should be. So I'm going to now, and this is the tidy afterflow, I'm going to go from implementing that feature to improving the structure so that future features like this are easier to implement. That's a little more speculative, but it's still a perfectly valid thing to do. If you say, this is how the structure should have been if I wanted to implement features like this, sometimes you go and do it to a certain degree. You can also go too far with that. Now, the last part of this picture is part of the magic of software development, which is sometimes understanding the structure gives you ideas for what features you should implement. So I was a fellow at a company called Gusto that does small business payroll, and we had ended up with two different tax calculators. And historical reasons, and it made sense at the time. Every single step made sense, but then it made sense to unify those two tax calculators because tax calculation in the US is you would not believe. So we unified the two tax calculators, and then somebody was saying, boy, wouldn't it be nice as a marketing feature to just on the homepage at Gusto have something where you could type in, here's the gross salary and here's the details of this person and how much would the paycheck be? And if people want to type that in by manually every month, well, fine, that's fine. But before that unification, we'd have to write another tax calculator. But because we'd improved the structure, it was just easy. Of course, we can implement that feature on the homepage. And so the structure itself gave ideas. And 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 this is where I'm going to use the word naive. This is where the naive split between a product organization and an engineering organization loses value because sometimes the structure of the system is a source of ideas. And the only people who are really going to understand that structure well enough are the people who have to interact with it daily, which are the programmers. So uh, the observation that many people make over and over again is we spend too much on this loop up here, and we spend too little on the structure loop down below. With technical debt, and we need a refactoring sprints and whatever. All of that is a way of we need to move more of the investment to structure stand. Um, that's very difficult organizationally because these features are extremely visible. Everybody can see them, everybody understands them, the customers like them, they're very visible, they're very legible in a seeing like a state sense. And these structure changes are quite invisible. The only people who really appreciate them are the programmers who have to deal with them. Uh, we know that if we don't invest anything in the structure, we're going to be dead in the water at some point, but tomorrow maybe. So today, let's just cram this extra feature in. So when I say empirical software design, when part of the message is do it later for anything speculative, but part of the message is do it sooner, invest more in the structure as you go along. And this is a tenet of extreme programming from way back in the day. Um, okay, so we have the economics of software, survival, followed by a balance between net present value and optionality. And then we have this flow from ideas to features, which involve changes to the structure at the same time. Now, net present value lives up here. Cost savings, every feature that you implement should either generate revenue or reduce costs. Um, the structure changes that we make create optionality. And so chronically, businesses over index on net present value and under index on optionality. Another part of structured design is observation. Now, I remember this from when I was in college in the 70s and early 80s. Studies showed that we were spending 60% of software development dollars on maintenance. Oh my goodness, what are we doing wrong in development that we have to spend 60% fixing it? And uh, the one direction the software development as a whole went in was let's do a better job of initial development so we can reduce the maintenance costs. Now that never made any sense to me, and by the time I came to extreme programming, I turned that completely on its head and said, what would it take for us to be able to spend 100%, 99% on maintenance and almost none on initial development. Um, but the observation in the structured design book that I call Constantine's equivalence is the cost of software is approximately equal to the cost of change. That is, that initial development, we don't really care about that. I'm going to go to a smaller pen. Okay. But the cost of change, all changes are not the same. This is an interesting observation. The cost of change is then approximately equal to the cost. Some changes are bigger than others. Lots of changes are just we go twiddle for a day and we're done. And then all of a sudden, one of them is going to blow up. So these jackpot changes dominate the total cost. If we add up the big changes, that comes to more than all the little changes combined. So how do those big changes happen? The cost of big changes is approximately equal. Now, how did the big changes happen? That's the observation. Remember, they had two piles of programs, one of which one pile was easy to change, one pile was hard to change. And what they noticed was the the hard to change programs, when I made a change here, I'd have to make two changes there, and I made a change there, and I have to make four changes there, and. And they called that concept coupling. So what makes change, the big changes big, is this propagation of change from one element in the software to another element of the software. And like an avalanche, exactly like an avalanche, it's the same mechanism causes these big changes as causes avalanches, causes income inequality, causes hurricanes, causes all kinds of these sort of jackpot, rich get richer phenomenon. And so if the what we have here is the cost is approximately equal to the coupling. And this is Constantine's equivalence. So if we want to manage the cost of software, we need to manage the coupling in the software. And coupling is this sense of, if I change this, I have to change those things too. So two elements are coupled. So if I'm going to use kind of a pseudo mathematical notation for this, if element one and element two are coupled, is defined as whoops. With respect to a particular change, that's an important part of this, is defined as changing E1 implies changing E2. So, for example, take two functions. Two functions, a called function and a caller function, are coupled with respect to changes to the name of the called function. If I change the called function, I have to go change the caller too. So that's coupling. But not all changes induce this coupling. They don't trip over this. If I change the formatting in the called function, then the caller doesn't care. So it's important to note what kind of changes that we're making at any given time. And one of the challenges of and analyzing coupling is that any two elements in the system can potentially be coupled. So I remember a time at Facebook where there were two services and they happened to occupy the same physical rack. So one was like ads, another one was a feed. They just knew absolutely nothing about each other. And you might think, well, I can change one service without having to worry about changing the other, except they shared this same rack and each rack had a network switch on top of it. One service changed its backup procedures. Instead of doing incremental backups daily, it went to a complete backup once a week. And during that complete backup, the network switch on the top of the rack was completely saturated. The other service would go down every Sunday for a couple of hours. How? We didn't change anything. Nobody changed anything. And yet the services were coupled. So one observation about coupling is very difficult sometimes to see uh, that two elements are coupled at all. And sometimes you can get rid of the coupling. In this case, they got rid of it by introducing a marketplace on network bandwidth, to put it very abstractly, so that no one service could dominate a shared resource like that. But that was a difficult change. So I'm going to add here another term to this cost, which is the cost of decoupling, which can be difficult, can require insight, can require inspiration, and is just a bunch of work. So what we want to do if we want to manage the cost is we need to look at the cost of the coupling and look at the cost of the decoupling. Since coupling is at n squared in the number of elements in the system, any element is potentially coupled to any other element. As the system gets larger and larger, the complexity of even doing that analysis becomes prohibitive. And that's where the concept of cohesion comes in. So cohesion, and I'm just going to go with the definition first. Uh, an element, we're going to call it cohesive with respect to the change, with respect to this change, if all of this, if changing any sub-element, let's see, I'm trying out a new formulation for this, so bear with me here. If changing any sub-element implies changing all the other sub-elements, let's see, what do we want to call this? Changing all the other sub-elements. So let me get concrete for a second. I have a big function. I need to change two lines in the middle of the function. That function is not cohesive because I have to change two lines. I have to change them both at the same time, but I don't have to change the other 40 lines in the function. If I pull out a helper method, if I extract a helper method that's just those two lines and nothing else, now I have to, that helper method is cohesive because I have to change both of them at the same time. And there's nothing else. The beauty of it is there's nothing else I have to analyze. There's nothing else I have to understand. So that's cohesion. Cohesion is coupling reduced in scope. And this took me the longest time. So I told you I started this quest to explain structured design in 2005, and I didn't publish Tidy First until 2023. So what took me so long? It was explaining cohesion because I had I could explain, like I had the definition, but I couldn't explain, it's like an element is cohesive if all of its sub-elements are coupled, but isn't that bad? Don't we not want coupling? And here's the thing, this is a compared to what situation? If I have to change two functions in one file, that's better than having to change two functions in two different directories. And I can almost always increase cohesion. As I said, analyzing coupling, this n squared problem, it gets more and more difficult. But improving cohesion, oh, I have these two lines in the middle of this big function that's not cohesive. Can I improve the cohesion of this? Sure. I just have to do local analysis. I don't have to look at the entire system to understand how to improve cohesion. Oftentimes, improving cohesion is the first step to understanding how to eliminate coupling also, because I've made those changes, and now the changes happen in a smaller scope, then I'm able to understand, oh, and here's how I can eliminate this coupling entirely and reduce the overall cost of the software. So that's those are the big aha moments for me in reading structured design and then trying to explain it to a modern audience. I'm going to end with one more thing, which is a cool piece of theory that still just flabbergasts me. I can't every time. Anyway, here's the thing. Remember we talked about the changes and the way that changes are not evenly distributed in cost. So if we were to plot the number of changes and the cost, what we would see is we have a whole bunch of changes that are very cheap to make. And we have one change that's just enormous and gigantic. And the way this graph fills out is it looks like this. We've got a bunch of changes here that are really cheap, and then half that many changes that are half that much, and half that many changes that are half that much, and so on and so forth. If we change the axes 1, 10, 100 to logarithmic, this is the magic. This makes an absolutely straight line. And this just blew me away. These kinds of distributions happen everywhere in software. Uh, so the cost of changes, the cyclomatic complexity of functions, you're going to have a whole bunch of cyclomatic complexity one and then one, you're going to have this one monster out here. Um, the runtime of test cases, we have a whole bunch of test cases that are blazingly fast and one really slow one out here, which brings up a fun party trick. If you tell me the speed of your 10 slowest tests, I can tell you how many test cases you have because I plot here, 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 and then I extrapolate back and I can tell you to within a reasonable accuracy how many test cases you have total. These, and this is a power law distribution. Power law distributions are created by any process of preferential attachment, where, for example, more complexity begets more complexity. Let's say we have to add an if statement somewhere in the code base. We are more likely to add that if statement to a function that already has a lot of if statements than we are to add it to a function that doesn't have any if statements at all. More likely. It's not perfect. But if that's the process, if we prefer attaching complexity to existing complexity, we're always going to get this kind of a power law distribution. So what makes this magic to me is if we have a power law distribution, you can't change the fact that you have a power law distribution because, and I'll get to the because in a second. We can't change the fact. What we can do is have some influence over the slope of this. So we can change the slope of this so it's much steeper. That means we have to have many, many more of these tiny elements in order to have the most complicated element being less complicated than it would with this previous slope in the distribution. Keith Braithwaite did a study of open source projects. Like, how do you implement that? How do you change the slope, the alpha? Keith Braithwaite did this study of open source projects, and he discovered that the ones that had been developed using test-driven development had a steeper distribution of complexity than the ones that had been developed with writing tests afterwards. That's the kind of thing that needs tons more research. So if you're looking for a research project, that would be a direction to go to look. And this brings me to my final point. And this is something a point I'm going to be making in the follow-on book to Tidy First, called Tidy Together, which you can see preview chapters of at my newsletter, tidyfirst.substack.com. There, end of commercial plug. Here's the startling for me statement is software is grown, not assembled. And this is where I think the different, not assembled. There we go. This is a big difference between empirical software design, this style that I'm exploring, and much of the writing that I see about software design coming from other sources. There's this idea that we can design the software however we want to, and it's not true. There are these powerful forces like preferential attachment that we cannot escape. And if you look at the data for the distribution of complexity, however you want to measure that, it it's not consistent with this assembly metaphor for how software is designed. And whether we're talking about top down or bottom up, that's those are both assembly style of metaphors. The style I'm talking about, this growth style, is it's like a tree grows. You start with one cell and then it splits into two cells and they differentiate, and the cell on top splits into cells that start to make a little leaf, and the cell on the bottom splits into two cells that start making little roots. And and mostly design, the way the structure evolves is as differentiation. So we have a thing, it gets too big, it splits into two things. The two things are heterogeneous. And then those things get bigger and then they split and split and split and split. The one addition we have in software is every once in a while we have this unification step where we have differentiated, and we say, oh, this thing is almost like this thing over here. So I'm going to take the parts that are identical and separate them out, and then I'm going to unify those two things. So software in the empirical style, software design is a process of differentiation and occasional unification. And that's very different. That leads to very different expectations for timing, pace, motivation for software design than you get if you start from an assembly metaphor. And so that's the prepared materials that I have. I've been carefully not reading the fact that we're getting a whole bunch of questions coming in. So I'd love to take the rest of the time and answer questions. Margaret Ann, would you please tee up a question for me?
Great. Thank you so much, Kent, for an incredible talk and an incredible audience as well. Very interesting discussion in the chat as well as the Q&A. The question that got the most votes, and perhaps is the hardest one to answer, and I may couple this with another one, is how does AI fit in the design and economy of software? And maybe it relates a little bit to another question that also got a lot of votes, which is, does an overemphasis on speed lead to technical debt?
Okay.
Yeah, the second one,
Okay.
let's couple that.
Which one do you want me to answer first?
Let's start with the first one. How does AI fit in the design and economy of software? I see my view just changed. Sorry, that second question didn't go with that one.
Okay. So the how does AI? This is interesting. I have finally caught the vibe coding bug. I kind of resisted for a while, and then I saw some people doing it, and I thought, "Well, I can do that." And I'm loving it. By the way, if you're all exploratory, if you have projects in the back of your head that you just have wanted to work on and you just couldn't, boy, pick up augment code, pick up cursor, give it a try. So much fun. Anyway, so I have been running into the limits of uh, augmented coding when the system gets too complex, when there's not enough structure to the system, the agent runs out of capability of making changes successfully. That's way past my ability to make changes if I was doing it on my own. And so, open question. Are there designs for the software that would be good for agents that would be bad for humans? Like at some point, if we're just going to make feature changes to the behavior of the system through agents kind of doesn't matter whether the human understands it or not. We're not there yet, but open question. I would prefer one where it's easier for me to understand and easier for the agent to manipulate. Um, there's also the question of timing. Agents are happy to introduce complexity just to get a feature completed, and that's a function of how they're trained. The models that are being like Claude Code are trained to get something done. So they're kind of like a college junior. They want to get an A on the test and they don't care if they have to cheat to get it. So a lot of as the augmented coder, a lot of what I'm doing is actually putting guardrails in place and saying, no, you can't do that, and you have to pass this test, and no, you can't comment tests out, and wow, there's this duplication I'm seeing. Unify these two things. Now, some of those structure transformations can be done by the models, which is an interesting, not yet explored. I had somebody told me they or demonstrated that they'd taken the tidyings, the tiny little cute fuzzy little refactorings in Tidy First. They'd taken those and put them into Claude Code, and they could just say tidy this function, blah, 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 and it would do something usually quite reasonable. As the models get more and more capable, we're going to see the ability to do bigger and bigger structure changes, more and more ambitious structure changes. And I don't know how far that's going to go. Another open question, definitely worth it. I'm trying now with the way I use uh, models for coding. I'm trying now to make structure changes, not just say implement this feature, implement this feature, implement this feature, because what you get is a gigantic mess. Did that answer the question or address
Yeah,
the question?
yeah, it answered it pretty well. I mean, I think the economy piece is still kind of hard to figure out. We'll probably come back to that. But there was also another question about vibe coding. And actually in the question, and you kind of answered it, but when will this foolishness end of coding? And and we've chatted about this, Kent. I know, what a fan you are. So you kind of touched on that. Maybe
No,
later.
it's worth answering. When will the foolishness end? It's if you're thinking it's foolishness, you're resisting like I was 3 weeks ago, and it's definitely not foolishness. Uh, if you're not ready to try it yet, that's fine. There's no shame in that. I mean, go back. I published a piece on the Tidy First newsletter about the adoption of hybrid corn in the 1940s. And from which we get the crossing the chasm model and so on. Uh, Innovation diffuses at human speeds, not at technical speeds. Um, when will this foolishness end? It's a beautiful way to put the question. It would be nice if it just went away and we could go back to how things were, but this genie is out of the bottle, and I can implement stuff that I imagined the effects of implementing it quite well, and I could not for the life of me implement it. And now I can sit down and have something that's actually working, just in time Bitblit compiler. Oh, sure. And it takes knowledge. What it means is that your ability to pick goals and your ability to break down tasks is much more highly leveraged than it used to be. So it's not all bad news. Um, but still, the models, uh, I had one yesterday. I said, well, go implement this feature, and it went implemented the feature. And I looked at the implementation, it was completely fake. It was just random numbers generating some text. And I'm like, that was not it. So you still have to watch these the models like a hawk if you're going to make progress.
Thanks, Ken. Good answer to that question about vibe coding. More to come on that from
Oh,
you.
oh, oh, wait, wait, wait. One
Oh,
other thing. I call it
oh,
augmented coding. Vibe
okay,
coding was the perfect name, and it's so last week. So
okay.
I think this is the
I like that.
purpose of this is to augment the kind of thinking that people do.
Love it. Love it. Much prefer that word. Um, Another question that came up, and you've kind of touched on this a little bit as well, but doesn't overemphasize on speed or an overemphasis on speed lead to technical debt?
Yes, and it should.
Yeah,
And it's because of survival.
yeah,
That is the point.
yeah.
So the I have this model called 3x, which talks about how you have in any kind of S-shaped growth curve, this logistic curve, how you behave down here should be completely different how you behave here, which is completely different than how you behave up at the top. So I call those explore, expand, extract. When you're exploring, you don't know the half-life of any change you make is zero. So any sins you commit, it doesn't matter. And this is, by the way, where augmented coding really shines right now, is the ability to go from not having something to having something and being able to experience it. But it's a very different set of skills than, okay, this is growing so fast, we just have to let's survive. By the time you get to this transition, survival is now assumed, and the all of the trade-offs that you've been working with completely change. I don't care from a if you like me as an investor, I don't care about technical debt in exploration because I'm just going to throw away most stuff. The one thing that's surprisingly useful when it starts to blow up, I can find plenty of resources to survive the technical debt. Uh, Time is of the essence, and I still want to just keep duct tape and band-aids and keep the system around because by the time I get to that extract phase, there'll be plenty of resources and plenty of time to address the technical debt. So as far as I can see, the natural state of a project is uh, janky, and that's fine. If I try to make it perfect all the time, I reduce my chances of survival. It is as you know, the kind of as an engineer, I don't like that answer, but every project that makes it to maturity has a bunch of technical debt. Huh, maybe that's part of the process.
Great, thanks, Ken. And actually, you touched on something in your answer that's a good segue to the last question because you talked about the 3x, right, on these curve and maybe the different skills, right, that are required at different levels. So this next question is, why is it still important to learn good software design with with the arrival of AI and more specifically LLMs? Should we shift the paradigm to build AI systems instead of traditional OO software systems?
The you can't escape that the exponential cost curve. The constant may be lower or higher, whichever. Your models may be able to deal with more complexity, but they can't deal with exponentially more complexity. And so we're back to having some balance of investment between the features we implement and the structures that we use to implement those features. Uh, just because you've got a model doesn't mean you can deal with infinite complexity. That would require infinite electrons, which we still don't have. So that's the reason that design is still this is a speculative, but I'm pretty sure about it. Answer is the design still matters, structure still matters because eventually you run out of the ability to consume complexity and continue implementing features. So I want still to have some balance between feature development and structure development, even if I'm augmented coding.
Great. So we have actually 40 open questions, and I'm hoping we'll get to a couple more before
Okay.
we shut down. But this next one kind of follows on a little bit, asks, what do you think about specifications and formal methods in software development? For example, in designing or distributed systems, you might save a lot of headaches, right, by using formal methods to model messaging and invariance. What are your thoughts on that?
If you're solving a known problem like multicast, or like something can be solved by a fairly well understood technique, th then it's fine. The challenge is when those formal methods prevent making or defer making changes. So a lot of the trouble I've had with formal methods is, okay, we have this specification for how the whole thing should behave. Oh, now we want to, and we do a bunch of work to prove a bunch of properties about this system that we have, and then we want to make some tweak to it. Now we have to start all of that process over again. It assumes that we're not going to learn anything along the way. That doesn't mean that specification is useless. If we have known problems, then going and doing a good job of solving that can be a solid base for future changes. And I want to have the option of doing that. One of my augmented coding projects is a special purpose database, and yeah, I need to do careful, thorough analysis because I want durability and resilience. Okay, well, I'm going to have to go prove some properties. I want a concurrency model that lets me uh, work in parallel threads. Okay, so I'm going to have to do a bunch of work on the concurrency model. I'm going to have to prove some properties before I can do this. I'm not just slapping stuff together, but I want to space that investment out in time. If I can defer some of it, I'm going to defer some of it so that I improve the net present value. But at some point, let's say you've built a system, there's some janky stuff, you figure out the structure that you wished you had, you go and implement that structure. Now you have new options for change. So that at that point, it can be really valuable.
Great. Thanks, Kent. I'm going to sneak in one more question. I really like this one. I think you will too. XP works extremely well in a team because we can support each other, compensate our weaknesses, and celebrate together. In the modern world, it's really hard to work as a team and share a goal. And now there's many forces that split us apart, such as AI. It seems it may make developers more separated and that they work more in isolation. What do you think about this effect of AI on XP?
A legitimate, reasonable concern. AI doesn't have to separate us. The way it's currently implemented, you probably will. But there's nothing to say that I can't have a tool that says, oh, you're making these kind of changes to the system. You should talk to Margaret Ann. She's making similar kind of changes to the system too. That's well within the capabilities of models to notice that kind of parallelism. Why don't you start a conversation group around these kinds of issues that you're both responding to? So it's a choice whether or not to form communities. I think the bigger issue is that the organizations we work in see community as a threat and try to reduce it instead of trying to foster it. And that one, that's, I mean, kind of out of scope for a programmer, except I can notice that the organization I'm working for makes it more difficult to collaborate, and I can choose how I respond to those incentives.
Thank you so much, Kent. Great way to end your talk and discussion. There's lots left, maybe some ideas for you to answer in your newsletter in the future. I'm sure we can share those with you. So I'd like to thank you again for your informative presentation and also the great answers to all the questions, and a special thanks to the audience as well. Oh my gosh, what a wonderful conversation in the chat and in the Q&A. This talk was recorded. It'll be available online, I think, shortly at learning.acm.org. And you can find announcements on upcoming talks and other ACM activities at learning.acm.org. And remember to fill out the survey. On behalf of ACM, Kent, and myself, Margaret Ann, thanks again for joining us, and I hope you can join us again in the future. And this concludes the talk.